Hello, this is Nature Matter 104, and our topic within this set of notes are pi and sigma bonds. And your homework assignment is going to be out of chapter 9, but I don't have my textbook with me, so I'll have to announce those on Wednesday the 29th. If you want to get them beforehand, you can definitely drop by the classroom tomorrow, which is Tuesday the 28th, and I can give them to you then. Anyway, so those will be due on the 31st. Okay, so we want to start off with some basics, and that is that a covalent bond can be thought of as a shared pair of electrons. Okay, so this is how we classify a covalent bond in first year chemistry. Very simple, shared pair of electrons. Another way to classify it, a covalent bond, is a covalent bond can be thought of as an overlap of two orbitals. Okay, so orbitals overlapping, very simple, to give us an area where there's a high likelihood of finding an electron. Okay, so you want to think of this when two s orbitals overlap. It's going to look like this. So we have a nucleus and we have a nucleus, and then we have an orbital, and these would be bonded atoms. And then we would have another orbital like so. And so there's this area right here where they overlap. So this is called the area of high electron density. Okay, and when an s and a p orbital overlap, so when an s and an sp orbital overlap, it would look like this. So we'd have our two nuclei, like so, and here's our s orbital, and then we know that an sp orbital has a larger lobe and then a little fishtail, right? So the area of high electron density again is at the middle there. S and P, or SP hybridization, excuse me, overlap would look the same, just with the two fish kissing, right, kind of. If we have SP and SP, then we'd have our two nuclei, like so. And then we'd have our little goldfish overlapping with another little goldfish. So it's kind of like they're kissing, I guess. They're overlapping in their faces. So there's our area of high electron density. Okay, so pretty simple. These are all examples of sigma bonds. And before we get started with that, we want to do a quick definition. And that is, if I draw two orbitals that are overlapped, for instance, like this, or two atoms that are bonded, and if we have orbital overlap as an example, and we're going to do an S and an SP. There's this imaginary line that runs between the two nuclei. So the imaginary line that runs between the two nuclei and that's called the internuclear axis. Okay, and so that's this line right here. And when the area of high electron density is on the nuclear axis, the internuclear axis, that's called a sigma bond. And the little symbol for sigma that's used to describe those looks like that, kind of like a sideways little music note. I often write the uppercase sigma as well, but I think in most chemistry textbooks they use the lowercase sigma. Okay, so you want to remember that all single bonds are sigma bonds. Okay, and then the other thing that you want to remember too is that in a multiple bond situation, one bond is always a sigma bond. It doesn't matter which one you choose, but one of those bonds will always be a sigma bond. Okay, so that takes care of sigma bonds right here. These are all examples of where we have the area of high electron density right on the internuclear axis. Okay, so we're gonna move on to pi bonds. Okay, so pi bonds exist when the area of high electron density is above or below the internuclear axis. Okay, and this would be an example of a situation where there's a pi bond. If we have two adjacent p orbitals overlapping, for instance, and our area, here's our internuclear axis right here, our little line, and our area of high electron density, there's two of them, so this would be like a double bond. These would be pi bonds. Okay, and so anytime that you have these p orbitals overlapping, they're going to be pi bonds. So any bond in a multiple bond situation is a pi bond, except one of those bonds, which will always be a sigma bond. Okay, so for instance, let's take a look at, as an example, we would be asked how many pi and sigma bonds in this molecule. And then you can also be asked as a follow-up question, how many electrons are in pi and sigma bonds in this molecule. And that's really easy to figure out. So let's say, for instance, that we're going back to acetic acid. We talked about acetate earlier, but here would be our Lewis structure for acetic acid, like this. There's our CH3COOH. And if I want to count up the pi and sigma bonds, I'm just gonna make a little list for myself here. That sigma and pi. Remember that sigma bonds are all the single bonds and then one of any double or triple bond that's present. So I'd go count them up. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7 sigma bonds. And we have one double bond here, and so one of those is going to be a pi bond, so this would be one pi bond. And then for the number of electrons, you just take and multiply your number of bonds by 2, because each bond represents 2 electrons, right? So in this case, our sigma, we would have 14 electrons involved in sigma bonds, and we'd have 1 involved in a pi bond. Oops, sorry. We'd have, for the pi bonds, we would have 2 electrons. 1 pi bond means 2 electrons. Okay, so I think that's it. Okay, thank you, bye.